Well, good afternoon, everyone. Let's get started with our second lecture. So in our first lecture, I, I more or less gave you my interpretation of what machine learning is, and then we implemented this perceptron learning algorithm, right? So that's how I like to start the class, but there are other types of learning that we didn't talk about, we kind of like excluded. So I just want to give you three of the basic types of learning that we'll encounter in this class.
Wait, before we start, I just had a question about the recording. Where do we go to access the recording from last lecture and
Oh,
lectures going forward?
on my YouTube channel, and that
Okay,
should be posted on Blackboard, but if it's not, I'll do that. Sorry about that.
no worries.
Okay, so these are the types of learning that you'll encounter in machine learning in this course. There's a few variations, but these are the three basic types. So first off, we have supervised learning. So supervised learning. So in this case, the training data contains explicit examples of the correct outputs. Okay, in the perceptron learning algorithm, which we implemented last time, that was an example of supervised learning. Right, we had the features of the iris flowers, and then we had the labels, whether or not they were Setosa or versicolor, right? So that was supervised learning. And the majority of this course will be on supervised learning. Okay, so though we will touch on the following two subjects as well. So unsupervised learning. I'm just going to go ahead and omit that for the sake of space. Unsupervised learning. The training data. And when I say training data, I mean the D, right? The D from last lecture, the collection of all data that we own, right? So the training data contains no labels for the output. Okay, so this is a much different situation than we encountered last time, right? In fact, it seems kind of odd that we could even say anything about the data if we don't have the labels, right? Like if we have a bunch of features and we have no labels, how could we ever make predictions in the future, right? It turns out there's several clever ways to do this. A lot of them fall into the lines of clustering. So you cluster the data when you don't know what the labels are. And finally, we have reinforcement learning. Reinforcement learning. So here, the training data does not explicitly let's make sure, yeah, that's what I'm going to say. Does not explicitly contain the correct outputs for the features. So this you can think of as, like, for example, suppose you're playing chess, right? And you have possible moves that you can make, and those are your features. You have no idea if that's going to be a win or a lose for Maple, right? But if you play that move and you know that you played that move, you can find out down the line if that was a good move or not, and give it a label +1 or -1, right? So this explicitly just means that even though it's not given to us directly, we can use the features that we have to infer what the label of the feature is. Okay. And again, all of these models fit into what I drew last time, which was that we have our feature space, X, and we have our label space, Y, and we will always have some subset of features where I label that by D sub X. Okay. So the data that we have, I always use D, and it looks like this. Okay. Now, in supervised learning, each of the labels that we have for our features, it would be all of this step Y. In unsupervised learning, we don't know anything over here. We just have features. In reinforcement learning, there's an intermediate step where we use the features and then we have to do some processing to then find the labels. But the goal remains the same, by the way. The goal remains, so this is D sub X. The goal still remains the same, to find our target function f that maps x to y. And it's always the case that f, if you put in your x, you get your correct label y. But as I mentioned last time, we're going to talk about today, f is unknown. Okay. So these are the three main types of learning that we're going to encounter. They all fit into the model or the diagram that I drew from the first lecture. And I encourage all of you between now and our meeting next week to look up definitions of these, see the varying definitions of them, and see the varying contexts for which they're used. Okay. In particular, it might be kind of fun for you to look at reinforcement learning because that's where, like, the state of the art is right now. It's one of the oldest types of learning, but it's also where the future is. For example, if you've heard of AlphaGo, this, like, I'll send a documentary to you. You'll see how reinforcement learning can be used to train computer programs to play games. There's one example. Okay. So these are the types of learning. I wanted to mention these before we moved on. But now we're going to move to a very fundamental question that we need to address before moving forward. In particular, why should we expect this partial data set of all of our features to tell us anything? Why should we expect that? And again, we have to remember that the goal is to find, so our goal is to find a hypothesis G that approximates F, right? So F is defined on all of X, right? So if we put in a new point, call it like X, right? Our goal is to have G take X to the correct label, right? That was the goal that we set forth last class. But is it even reasonable to think that we can do that? Right? If we think back to the previous lecture where we implemented the perceptron learning algorithm, we trained it appropriately on the data set that we had, but how do we know that says anything about the data that we haven't seen? How do we know? Can we ever hope that that's the case? So let me move my little desk real fast. I'm gonna unpause the recording. Okay, so when considering whether or not it makes any sense to use a partial data set to say anything about the full data set when learning, let's consider this problem here. So as we saw with the perceptron learning algorithm, we had labels either -1 or +1. So we're going to stay with that framework for now. So the set of features, X, consists of all triples of zeros and ones. Okay? And the labels for those triples are either -1 or +1. And I denote that by negative or positive in this grid. So right here, that in that green box, you can probably not tell it's green, but that's my set of features in my data set X, right in here. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Okay? In the labels, we also know, so this is the supervised learning task. So here, this column right here, these are our labels. So we know the labels for that data. So 0, 0, 0 is -1, 0, 0, 1 is +1, 0, 1, 0, +1, so forth and so on. Okay? Does that framework make sense? That this is our data features, these are our data labels? Yes, no?
Yeah, that makes sense.
Okay. So now, suppose we're able to train an algorithm to find a G that we want to approximate F, right? So here's G, right here. This column right here, that's the G that we found. And on the data that we have, we predict the correct labels. You see that, like that matches up, right? Okay. So this would be like the case last class where we used the perceptron learning algorithm to predict the perfect labels on the data we had. Right? It matched up. So before we signed off last class, we were excited. We were like, yes, we predict the right stuff, right? We predicted the right labels. But we only were looking at the data set that we owned, right? So let's, again, think back to finding the target function F, or approximating it the best way we can. So here, these are, so F1, F2, F3, F4, F5, F6, F7, F8. These are all functions or hypotheses that match up with that input data. See how these are, all these rows here for G and all these F's, they all match up, right? So that means that, okay, if we're trying to find F and we truly don't know what F is, then any one of these functions is a possibility for us to be approximating. Any one of these, right? Like F, does that equal F1? Does the target equal F2? Dot, dot, dot. Does the target equal F8? The last one? Well, let's look at how these functions differ. This function matches up with our features and has the correct labels, but then has negative, negative, negative. This one, F2, has negative, negative, positive. This one has negative, positive, negative. And these are features outside the data set that we own, right? These are all features that we've yet, it's like, I know the light's blurring it, but like right there, that X that we picked back on that board, it's like if we pick any one of these, we want to be able to predict what the target function would predict. That's our hope, right? But notice that all these functions match up with G, but outside of the data set that we own, they all differ. So which one is it? If we really don't know what the target function is, any one of these should be G. Like, of course, we can make G match up on our data set, but any one of these, like, if I shift negative, negative, negative right there, then G is equal to F1, right? But it's just as valid to say that F2 was the right outside of the data set. It's just as valid as F3. It's just as valid as F4. How can the data we own tell us anything about the data that we don't know? Which of these could G possibly be, right? We decide, so G is going to meet up on our data set, but it's going to have to take a form, one of these. Which of those could it be? They're all different. Does that seem concerning?
Yes.
Right? Like, it should feel off-putting because just like with the iris data set and the perceptron learning algorithm that we implemented, we did this on the data set we had. But who knows what those weights we would have trained would have said outside of it? Which of these functions could it be, right? A lot of functions can match up with this on the data set, but then they can all be different. So that's why it's concerning, because we need to say that what we're doing is meaningful, right? So, okay, let's move back over here. I'm gonna pause the video again. Let's resume. So, in order to understand this problem of learning more, we're going to revisit a notion from statistics. And this is why statistics is important in terms of machine learning. So imagine you have some bin. Okay? And in that bin, you have, say, black marbles and white marbles. Okay. And okay, those are like just black and white marbles, right? And then suppose that you reach in this bin and you grab a sample of capital N of the marbles. So you pull out a sample And maybe it looks like this. Something like that. Okay, and I promise you, this is going to relate back to learning. Even though we're talking about marbles right now, this will relate to learning. Okay, so I'm going to introduce some notation now. So I'm going to say let mu be the probability of selecting a white marble. Selecting a white marble from the bin. Okay, and I'm going to let mu be the fraction of white marbles in the sample. Fraction of white marbles in the sample. Okay. Now, many of you have taken statistics courses, a lot of them. So you should know that there is some relation between the probability of an event occurring in the sample and the probability of the event occurring in the population of the bin. Are y'all familiar with this notion that there is a relation? Maybe, maybe not.
Yes.
Right. And this generally falls underneath the category of, or not the category, but the realm of the law of large numbers. And in particular, for us, we're going to choose the Hopping inequality, since it's one of the easiest to understand. And since it's a bound and not a asymptotic approximation, inequality. And it states that the probability of nu, the distance from nu to mu, being greater than epsilon, is at most 2 times e to the power -2 epsilon squared times n, for a sample size of n in any epsilon greater than 0. So for a sample size n and any epsilon greater than 0. Now this is good. Now I know you might not see that it's good. So let me explain a little bit about this. So absolute value of the difference is like the distance between two numbers, right? And mu and nu are just numbers. So this is like this right here. So this is like how far is nu from mu, right? That's the distance. And this is saying the probability of this distance being greater than epsilon. So you pick any positive number epsilon, the probability of this being far from that, or greater than epsilon, is at most twice of a negative exponential, which is good, right? Negative exponentials, like So this is like a bad thing. We don't want u to be far from mu in this case. Our hope is that this is a close approximation to that. So this is like the opposite of that. This is bad. We want this probability to be small. We want this to be, to have this distance greater than epsilon. We don't want that likely to happen. So that's good because this probability is bounded above by a negative exponential, right? However, epsilon is typically going to be some small number, right? Like epsilon could be like 0.001. That's going to counterbalance the negative exponential if you plug that in, right? But you can counterbalance that with a larger sample size, right? The goal of the negative exponential to be small is to have the exponent not including the negative. You want that to be as big as possible, because then the value will evaluate as small as possible, right? But it still does give us a bound. And there's a detailed explanation of this on YouTube that I'll share with you. But for our purposes, I just wanted to show that there is a bound involving the distance from the probability of the distance from the sample nu to the bin mu being greater than epsilon. So in a sense, we can say that the probability of this being greater than a positive number, epsilon, is bounded but by something that's likely to be small. If you pick your epsilon and your sample size appropriately. Which means that in general, that's going to be close to that. And we can take larger and larger sample sizes so that if we take n really, really, really big, then this is going to be small, right? You see that if like n was 2 to the power 100, it's an unrealistic sample size, but that's still a number, right? This is going to be small. The probability of that being farther than that is going to be really small. It's not likely to happen. So we could take a huge sample and we're somewhat safe that that will be close to that, right? This should be from like a previous statistics class that somewhere you've seen, and this is like related to like the law of large numbers. That there's several laws of large numbers. Maybe the simplest one you can think of is that the sample mean approaches the population mean when you take the sample large enough. That's like another one of these things, right? Okay, this is saying something similar. So the idea is that we can, like, yes, some samples will be bad samples. Like you could theoretically take all black, right? You could, but the likelihood of that happening is going to be small, right? Especially if n is big. Does everyone, are all of you on the same page with me on this?
Yep.
Yes.
Okay, so how does this relate to the learning problem? Well, let's relate it. So so everyone should know that epsilon is a positive number, n is the sample size. That's the probability in sample of picking a white marble. That's probability out of sample in the bin of picking a white marble. So I can like erase this really fast. Okay, so consider a hypothesis H inside of our hypothesis space. If you recall the diagram that we had last time, we have this space of possible hypotheses, and the goal of machine learning is to search in there and find the best one that approximates the target function. We call that, once we find it, we call it G, right? So we're going to relate this to our marbles by way of a coloring process. So we're going to say, if H evaluated at some features equals the target evaluated those features, color the marble black. So color black. So that's if the hypothesis that we're looking at is equal to the target function at that given feature, or at that given vector of features, then we're going to go over here and we're going to color the marbles black. And then if H of X is not equal the target at the vector of features, color white. So notice now, so we don't know F, right? Just like we don't know mu, right? We don't know mu, and we don't know F. So once we pick F, or no, pick H. Once we pick H, we do get a coloring just like this, right? It's the same notion. Like we don't know, but there is some probability distribution of the colors in there. We do know over here, by the way, in sample, whether or not our target equals our hypothesis, okay? So next, I'm going to define two very important concepts. So as we search our hypothesis space, we find a hypothesis, and when we do, we have immediately in-sample error for that given hypothesis. And again, we're always picking capital N data points in our sample. Okay, and this is going to be, there's some special notation here. So this, with these bars right here, so this is equal to 1 when true, 0 otherwise. Okay, 1 when true, 0 otherwise. So looking at our new here, right? The H that we pick is going to color the marbles, right? So if the color was off from the correct color, we have 1 plus 1 plus 1, whenever that happens, divided by n. That's the same thing as the fraction of white marbles in the sample. It's the same thing. The in-sample error here is the same thing as the ratio of white colored marbles to the collection. There's n total marbles, there's white, right? And white is when our hypothesis isn't what it should be. So do you see that this is the same thing as that? Does that make sense? We good? No? All this bracket business says is that if it doesn't equal, it's a 1, and if it does equal, it's a 0. If this statement's true, you have a 1, otherwise it's a 0. So it's basically counting how many white marbles over the total number. Is that clear?
Yes.
Yeah.
So this is like a way of thinking about new. And then we have our outer sample error for a given hypothesis that we've chosen. And that's just equal to the probability that h of x is not equal to f of x. And this is like our in-sample probability of selecting the white marble. Or not in-sample, or in the bin, the me over here. Sorry. Okay. So again, when this happens for a given feature vector x, we color that marble white. So the probability of selecting a white marble from there, it's the same thing, right? Good? No? More or less okay? So now we can kind of discard these mu and nu. And talk about the following. For a given hypothesis H, we can use the Hopkin inequality. And we're going to look at the absolute value of the in-sample error for a given H minus our out-of-sample error for a given H. The probability of that being greater than epsilon for some positive number epsilon is at most 2 times the negative exponential, like that. But we can only do this, we can only apply this inequality after the marbles have been colored. Do you agree with that? Right? Like, well, not do you agree with that, but do you observe that? We picked an H, and then we got the coloring, and then it became transformed into this law of large numbers. But that was after we picked the H, right? So after we pick the H, we can then color the marbles, and then we can apply this probability and get that inequality. Which, by the way, we want this error, right, to be small. We don't want it to be greater than epsilon. We want our in-sample error and our outer sample error, we want those to be close to each other, which this will more or less give us a bound. Well, it does give us a bound, but for the appropriate choices of n and epsilon, we're somewhat assured it will be close, sort of, right? And again, this is a probability, it's a likelihood, right? It's not set in stone. It's possible that they could be very far apart, but we want the likelihood of that happening to be small, right? We want that and that to be close. But that's for a given H. If you recall the picture that I had, we were trying to find the best function G among all possible H's. So suppose our hypothesis set consists of something like M hypothesis. So let's call that like hypothesis 1. And then we uncolor all the marbles and we pick a new hypothesis call it H2. And then we can apply the complement inequality again. And that's the probability that for our new hypothesis H2, that in and out are greater than some positive number epsilon. And suppose we have m possible hypotheses. So suppose we exhaust out all the hypotheses in our hypothesis set, and there's n choices of them. Okay. Now each time we do this, we color the marbles, and we apply Hawking. Then we pick a new hypothesis, color the marbles, and then we can apply Hawking. Pick a new hypothesis, color the marbles, pick a hypothesis, or pick a new hypothesis. We do that n times, right? So G is going to be the function that we choose. Our final hypothesis, G, that we pick, is going to be one of these H's. It can be that H, or that H, or dot, 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 or that H. It can be any of those, right? It's just one of them, we're picking it according to the model that I drew last time. Just picking some H. Well, we can't say anything about this versus that one, any of this for our particular G, right? We don't know. All of these are going to be different, okay? But we just know that they're bounded above by these values in each instance of a hypothesis. So we can say that if you remember the probability of A1 union A2 union dot, 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 union AM, you sum the probabilities and you subtract off the intersection, right? That's the formula for the union of probabilities, and OR is like union, right? But if you don't subtract off, you just know that this is at most the sum of the probabilities. Right? If you didn't subtract off, you know that it's at worst case, it's like this, okay? This is bigger than if you would have subtracted off. So if I know that G could be any one of these hypotheses, so it's that one or that one or that one or that one all the way down, I know that the probability for G, so in sample error G minus the out of sample error for G being greater than epsilon is at most that plus that plus that plus that plus that plus that plus that all the way down to m. So I know that the G that I eventually pick is going to be at most 2m, the negative exponential. You're basically adding this m times for each of these m hypotheses. It's a crude way of getting a bound. It's very crude. Because like this could be far away from that, but it still gives us a bound on the in sample error versus the out of sample error. We want these to be small, and the probability of that being greater than any positive number epsilon is given by this upper bound. So what's the moral of the story? What this is telling us is that provided it's very important that our sample was randomly chosen in order for this to be valid. So the sample data that we own needs to be chosen randomly in order for this bound to be valid, which means in order for this bound to be valid. So how the data is chosen that you use is important. That's number one. How the data is chosen. It needs to be random. Okay? But if your data is chosen randomly from some unknown probability distribution, then we're guaranteed that the in sample error and the out of sample error is no more than this if we pick through the possible hypothesis that we are considering. Okay, so that's the moral of the story here. That we don't want this to happen, and the probability of that happening is at most this. So we know there's some hope that using the in-sample data that we have is going to tell us something about the out-of-sample data. That's where I started this lecture about pretty much. Is there any hope that what we learn on the inside will tell us anything about the outside? And it turns out, if n is large enough and epsilon, our tolerance is chosen correctly, then we're pretty much assured that this is going to tell us something. Right? Like, that's the whole point. Because this is bounded, because it's bounded by something that's in terms of a negative exponential, even though small epsilon is going to throw it off, even though that might happen, this bad scenario, the likelihood of that happening is at least bounded in a probabilistic sense. So that tells us that yes, like learning is feasible. There's never in a probabilistic sense. Yes, bad outcomes can happen, but so long as your data is chosen randomly, according to some probability distribution, then picking random samples out of the set of all features, right? Picking out randomly is going to tell us something about inside. So let me just cut this off. Now again, this is not the objective of this course. We're not going to spend a lot of time on these theoretical aspects. Some courses do, some courses don't. I just think that it's important just to observe that the in-sample error versus the out-of-sample error, the difference between those two is bounded. That's all that the past like 30 minutes was. It's bounded so we can hope that stuff on the inside tells us stuff about the outside. And by stuff, I mean information about the labels. So I'm going to draw those two diagrams again. So we have our target function f. We have our data d. So this is like our in-sample data. And then we have a collection of algorithms A. We have our final hypothesis G. Which is supposed to approximate F. So the new thing that we have is some probability distribution. We're going to run some probability distribution that generates our in-sample data. We have our hypothesis set here. And the probability distribution that we have also contributes to our target function F and how well our G approximates that target function. Okay. So this diagram is different than the book I'm using, but this is how I view it. Now, this is important to notice that, like, I think this emphasizes that the out of sample data, the data that we don't use, is vital to whether or not what we did meant anything. Right? So this, all right here is the general idea, general flow of how learning works. But how can we test this? Right? How can we get a glimpse of how well our hypothesis approximates the target? We'll never know the target, right? We never will. But how can we get a glimpse of how well that approximates that in a very real sense? How can we see how well it approximates it? Any guesses? Again,
Would, like you were saying, can you just, you'll never know the true value, but you can use like a confidence interval to get somewhat close to it?
well, I would say that what I'm trying to poke at is to get a concrete way of getting like something that we can literally test to see approximately how well we can literally test it to see how well our final hypothesis matches up to the target. So maybe I'm being a little vague with my wording, so I'm just going to draw a picture. So we have our data, right? So suppose we're in supervised learning, right? We have x1, y1, 2, xn, y. Okay, so we're familiar with this concept. So what we can do to get a glimpse, maybe, of how well our hypothesis approximates the target is to split D into D, I'll call it train, and D test. So now, if we do this, so both of these are subsets of D and they're mutually exclusive. These are disjoint sets of data. Nothing in there belongs there, nothing in there belongs there. The union is the full data set that we own. So we're thinking about like a real world scenario. We're given data, we know nothing about the theoretical aspects of what's outside of it. We're just given data. So now we can adjust this model here by saying that this is D-train. Okay. So instead of using the full data set that we have, we're going to use some pieces of it. And we're going to leave this out. D-test is also, you can think of it as like validation. So once we form our hypothesis G, we find the G that we want, maybe, or we find a hypothesis H from there. So we can ask ourselves, like, how well does H, the one that we're considering, perform on the test data? If we're satisfied, then we can pass that in as our final hypothesis. The H that we tested becomes our G, and that's the one that we passed in. So because we're always concerned with out of sample performance for our models, for our hypotheses, and we know that we know that it's possible that our in-sample hypothesis will perform moderately well on out-of-sample data. So how can we test that? We can test that by taking some random collection of our data that we own and train on that data. Once we've made our model, our hypothesis, then we can test that on the data that it hasn't seen, that we own. It's important to know that we own that data. We just exclude it from being used when building our hypothesis. And that gives us a glimpse about how well our final hypothesis does on the data that we haven't seen yet. And the more data that you have, the better. For example, if you have 70,000, this consists of 70,000 data points, then you could use 60,000 on train, and then you could leave 10,000 to test on. If your hypothesis performs well on those 10,000 in the test, you should be fairly confident you're doing okay. So this was the second motivation of today's lecture. Again, the first was just to give you a somewhat informal argument for why we can ever hope that our data will perform at all on giving us any information about the data we haven't seen. And now that we know that that's possible, it's important to kind of check to see whether that is actually happening. And you do that by splitting your data into train data and test data. You train on this collection, and then you see how well it performs on that collection. Okay? So, it might be a good note, not might be, it is a good exercise for you to program the perceptron algorithm on the IRIS data set, but split the data. Split the data into two sets, a train set and a test set. Train the perceptron learning algorithm on the train, and then measure its performance on the test. And you can do that by saying the error is equal to 1 over the number of points in the test times the sum. So this is like n prime. N prime is like the number of elements in the test set. This is equal 1 to n prime. So you form a hypothesis on the training, and then this is one error measure that you can look at. So does your hypothesis on data points in there, does that not equal the label for it? Because that is in our data set, so we know it. And then 1 over n times that sum, that'll give you the error on your out of sample data. Well, an approximate error to your out of sample data. So do that. Last time we did the perceptron on the IRIS data set, and we trained on the whole data set. But as we've seen, like that doesn't tell us how we're performing out of the data set. We know it's bounded by some number in a probabilistic sense, but how can you get a sense of how bad it's doing out of data? Well, split your data set, train on this one, and then test on that one, and this is your error. And again, that's that Boolean function here. If that's true, then it's a 1. It's not, it's a 0. It's false, it's 0. Okay, so I'm gonna go ahead and stop the recording here.